Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. Not all networks fit neatly into the broad categories of LAN, MAN, or WAN. In many environments, specialized network types exist to serve specific use cases, contexts, or spatial scales. These include wireless local area networks, WANs, personal area networks, PANs. Each of these is tailored to particular scenarios, some emphasizing mobility, others extending connectivity across buildings, and others existing for highly localized, often user-centric device pairing. Understanding these specialized network categories expands your ability to design, troubleshoot, and analyze complex network environments. These specialized types are directly addressed in the Network Plus exam objectives and frequently appear in scenario-based questions, whether identifying how a smartwatch connects to a phone or classifying a university network that spans multiple buildings. Exam candidates must be familiar with how these terms are defined and applied. They're not just labels, they reflect real architectural considerations, influence technology choices, and signal the scale at which specific protocols and devices operate. Mastery of these types ensures you can confidently distinguish network scopes beyond the standard LAN or WAN. A wireless local area network, or WLAN, is the wireless extension of a traditional LAN. It provides the same basic services, such as file sharing, printer access, and internet connectivity, but uses radio signals instead of cabling to connect endpoints. WLANs rely on access points that broadcast and receive wireless signals, creating communication zones for mobile and fixed devices. These zones allow laptops, smartphones, tablets, and other wireless-enabled devices to interact with the network without requiring a physical tether. WLANs offer several key features that distinguish them from wired LANs. First and foremost, they eliminate the need for physical cabling to each endpoint. This flexibility supports dynamic movement within the network area, enabling users to roam while maintaining connectivity. WLANs also use shared frequency bands such as 2.4 GHz and 5 GHz to manage access between multiple devices. Technologies like Wi-Fi 6 further improve efficiency by optimizing how bandwidth is allocated and how devices contend for airtime in shared environments. Security is a critical concern in WLAN environments due to the nature of wireless communication. Unlike wired signals, which are confined to physical cables, wireless signals are broadcast in all directions and can be intercepted by nearby devices. This makes encryption and authentication essential. WLANs may be configured as open, meaning no security, or secured with protocols such as WPA2 or WPA3. Authentication may be managed using pre-shared keys, enterprise-level credentials, or certificate-based systems. Without proper configuration, a WLAN becomes a significant security liability. A personal area network, or PAN, is a short-range network used for direct communication between devices typically associated with a single user. PANs allow smartphones, tablets, headsets, fitness trackers, and other personal devices to connect directly without relying on centralized infrastructure. The connections are temporary, peer-based, and often established automatically, emphasizing convenience over complexity. PANs exist independently from LANs and WANs, forming on-demand links between personal gadgets. Technologies associated with PANs include Bluetooth, which is by far the most common PAN protocol, as well as infrared and near-field communication, NFC. Bluetooth enables devices like wireless keyboards, earbuds, and smartwatches to communicate with smartphones or computers without cables. Infrared, while now largely obsolete, was once used for short-range file sharing. NFC allows devices to exchange small amounts of data with a simple tap and is frequently used for payment systems, ID badge readers, and mobile check-ins. Despite their usefulness, PANs have limitations. Their range is very short, often limited to just a few meters, and their throughput is much lower than LAN or WLAN technologies. PANs are designed to be lightweight, convenient, and low power, making them ideal for wearables and sensors, but not suitable for tasks requiring high-speed data transfer. They are also ad hoc by nature, lacking persistent structure or centralized management, which restricts their role to small, purpose-driven scenarios. A campus area network, or CAN, fills the gap between a LAN and a MAN. A CAN typically spans multiple buildings within a single campus, such as a corporate office park, university grounds, or medical center. These networks combine multiple LANs into a single, centrally managed infrastructure that supports seamless communication across the campus. The design goal of a CAN is to provide unified access, consistent policy enforcement, and reliable performance across a contained but expansive environment. CAN infrastructure is built on high-speed backbone links, often using fiber optic cables to connect buildings. Centralized control is a defining feature, with IT teams managing core routing, switching, and security policies from a single data center or network operations center. CANs may include wired LANs, WLANs, and even limited WAN connections to the internet or external sites. Access policies and address plans are usually standardized across the network, ensuring consistency and security regardless of location within the campus. One of the most important aspects of understanding specialized networks is recognizing how they overlap with one another. A CAN, for instance, is often composed of multiple LANs and WLANs. WLANs serve mobile users within the CAN, and those users may also operate PANs with their personal devices. Meanwhile, the CAN as a whole sits below the scale of a MAN, but may be linked into a MAN or WAN for regional or global connectivity. These categories are not mutually exclusive. Rather, they describe layers of function and structure that interact in meaningful ways. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. Each specialized network type is defined not only by its structure and scale, but also by the devices it supports. WLANs are designed to serve a wide range of endpoints, from laptops and smartphones to tablets, printers, and IoT devices. Their flexibility makes them ideal for environments with mobile users or changing device needs. PANs, in contrast, typically support short-range, low-power devices such as wireless headsets, fitness trackers, smartwatches, and other personal gadgets. These connections are often temporary and highly individualized. CANs support a broader infrastructure connecting desktop computers, servers, IP phones, security systems, and access control devices across multiple buildings. Management strategies differ based on network type and complexity. WLANs are often managed using wireless LAN controllers that centralize configuration, firmware updates, and performance monitoring for multiple access points. In larger networks, WLANs may also integrate with policy engines or authentication servers. PANs, by their nature, are unmanaged. They operate ad hoc, with connections formed on demand, typically without administrator intervention. PANs, on the other hand, require robust IT oversight. They are managed through enterprise-grade tools that coordinate routing, access control, bandwidth allocation, and infrastructure health across the entire campus. Wired LANs are frequently integrated into wired LANs to create unified enterprise networks. Access points act as bridges between wireless clients and the wired network, often connecting to core switches or controllers via Ethernet cabling. Once authenticated, wireless users are assigned IP addresses, usually by the same DHCP servers that serve the wired LAN, and can access the same resources, assuming policy allows. This integration supports unified addressing schemes, consistent access controls, and seamless roaming between wireless and wired segments within the organization. Addressing behaviors differ across PANs, WLANs, and CANs. PANs often use automatic temporary local addressing, such as Bluetooth link keys or ad hoc IP assignments for hotspot connections. These addresses are typically not routable and are only used for the duration of the connection. WLANs usually rely on DHCP, assigning dynamic private IP addresses that tie into the larger LAN or CAN infrastructure. CANs implement structured addressing plans to coordinate device identification, segment traffic, and support routing across various buildings and departments. Static addressing, or DHCP reservations, may be used for critical infrastructure, Troubleshooting in specialized networks requires an awareness of their unique vulnerabilities and dependencies. WLANs are susceptible to interference from physical barriers, other wireless networks, and electromagnetic noise. Issues may arise from access point placement, signal overlap, or misconfigured security settings. PANs commonly suffer from pairing failures, drop connections, or low battery disruptions. PANs may experience segmentation problems, routing inconsistencies, or uplink failures between buildings. Each scenario demands a distinct set of tools and procedures to isolate and resolve issues effectively. Security expectations also vary by network type. PANs typically have minimal protections, relying on basic encryption or device authentication like PIN codes. While this is often acceptable for personal data or temporary use, it presents risks in high-security environments. WLANs must implement strong encryption protocols like WPA3 and centralized authentication to protect data from interception or spoofing. PANs extend enterprise security policies across their entire footprint, often leveraging access control lists, VLAN segmentation, and monitoring tools to enforce consistent protection across buildings and services. The Network Plus exam includes terminology and classification questions related to specialized networks. You may be asked to distinguish between a PAN and a LAN based on a scenario or diagram, or to identify the characteristics of a CAN in an infrastructure layout. Other questions may test your ability to recognize WLAN deployment details or match technology types to appropriate use cases. Accurate classification depends on understanding the function, scope, and connectivity of each network type, as well as their real-world applications. Context is essential when analyzing specialized network types. A device type, connection method, or deployment environment often hints at which category is being used. A fitness tracker syncing via Bluetooth with a mobile phone is clearly part of a PAN. A corporate Wi-Fi deployment supporting mobile employees throughout an office building is a WLAN integrated into a LAN. A fiber-connected campus with centralized IT services and consistent policies across multiple buildings is a textbook example of a CAN. Being able to assess and interpret these cues will help you classify networks properly on the exam and in professional practice. Specialized network types fill the gaps that standard LAN, MAN, and WAN categories don't fully address. They adapt to personal technology needs, extended building layouts, and wireless mobility in ways that traditional classifications cannot. WLANs remove the limitations of physical cabling, PANs allow for quick, localized device communication, CANs unify distributed LANs across campuses into a single manageable ecosystem. By understanding these network types and their distinct roles, you strengthen your ability to architect and support networks that are functional, secure, and optimize for their environment. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.